I'm recording now. All right. Stop sharing. I'm gonna share the slides. And while I'll do that, can somebody tell me what does forward kinematic do? Like, we learn a method, right? But what does it do? What is forward kinematic? Okay. Okay. So when you say gives the configuration of the end effector, what does that mean? Position. Now, correct. So forward kinematic will tell you the position and orientation of the end effector. Now, how do we find that expression from the POE method? What was the principle that we could use that method? Yes.
We find screw axes for each joint, and then like exponents screw axes,
right,
like the angles, and then multiply those out.
Okay. And then you already know the initial position of the end effector, right? So you want to see. So what is this screw axis representing? What does the screw axis represent? And the angular rotation or velocity and linear velocity, right? So you multiply these and then multiply by home position, initial position, right? Position, and you get the configuration. So you're using velocities to find the position. Just like if we have a car, I say, hey, this car is going 25 miles per hour. How long does it take? Like, what is the position of car in 1 hour or 60 minutes? You just time multiplied by velocity, or velocity times time will give you the position, right? So here, what is time? Where do you see time in this forward kinematic expression? Yes, theta, or our joint variable. So if it's charismatic, it's just d, right? So theta and d are joints are variable through time. So from 0 to 10, instead of just having a number for time, we have that number for our theta or joint variable, not prismatic and revolution, right? So in that expression, t equal to that big exponential expression, the variables are your theta 1, theta 2, until whatever, how many joints you have. If you want to have a numerical value for your end effector, you plug in how much each joint rotated or moved, and it will give you a 4x4 matrix with value. Then you can grab the rotation card, find the rotation and angle, and you can grab the position. Make sense? Now, we are going to use another method that gives us the same 4x4 matrix, but using a different method. If you remember, in POE, we said we are going to consider a fixed frame, and we fixed it at the base, right? If you're reading your book or you're watching the videos from the author book, there's another way of doing this. Put the fixed frame to the end effector and calculate everything from end effector perspective. To me, it makes sense if you put it on base, because you always are looking at base to start moving, right? So that's why I only taught you that one. So finding a base frame, and then every time something is rotated, because it's with respect to base frame, you pre-multiply, right? Every single frame with respect to base frame. Now, the new method, DH convention, says that, you know what, you could find it another way. You can find the relative rotation or translation between the matrices, between the frames, multiply them, and then find the same solution. It should be correct. How much this joint rotated with respect to this joint, how much these rotated. If I multiply all of them, then I have my end effector position. It should be the same thing. So this new method, like DH convention, will give you the same result if you simulate. The matrix might not be the same, but when you're simulating, starting from one position going to another, it will give you the same position and orientation for the end effector. All right. Now this method is a little bit funky in terms of you have to assign all the frames yourself. So in the previous method, I gave you all the frames, right? So this method, usually DH convention is used when you are assigning the frames yourself. All right. Assigning frame ourselves has a good benefit. We can eliminate a lot of calculation by putting frames in a specific location. That creates a lot of zeros in our calculation, so we just have to do less calculation. So a lot of industrial robots use this. The code comes with the robot, and they're using this in their code. Once you learn both, you can choose whatever. If you're in robotic board, you can use it. Now, I will post the solution to the practice quiz or CP10, but this is in your book. So if you're following textbook, you can find this. I'll post that, but things that you should have done, create this table. There are QI. Actually, it is in the annotated version too. Create M, create QI, find omega I, VI, and then you had to find SIs, which is the screw axis, and bracket SIs, which is the matrix representation of the exponent coordinate. And then you had to say now theta is e to the power of S1, theta 1, ES2, theta 6, and this is your expression. You should have stopped here. All right. And I said you can leave it just like that. Now, do you remember how do we calculate each of these? Because this is expandable. Now, if you want to actually get to numbers, you have to expand it, right? You remember where to find it? An honest answer is no, and that's totally okay. So if you look at lecture 12, so after I introduced Rodriguez formula, the closed form of this expression is this, e to the power of S theta. So you found S1. Theta is your variable. You have to create this matrix. This will be 4x4 matrix. Then you plug it in that forward kinematic expression. You see that how complicated the calculation are using POE method. Now, given that you code, the computer will do all of that. But there's a lot of calculation afterward. This method, you put work up front. The calculation is the easy part. All right. So I'm not asking you to do this for exam or anything. We're going to use this for the coding assignment. I just wanted to show you that we have done this. Yeah, I have showed you that. All right. Any question on that? What? This is end effector. It's like a fork. So you consider another frame here. Oh, this is a prismatic. So if it was prismatic, it would show you like an arrow that it moves this way, would be theta whatever instead of that. But it's fine. You probably won't lose much points, but pay attention to the thing is, this is the diagram. You should be able to read the diagram. All right. So I think in your homework, you actually see a prismatic in one of the questions. So you have to pay attention to that. I think that's what you did in your exam. Prismatic, if you remember, always will be a disk. Like if it is a box, there will be a disk in front of it to show you that it's displaced. I think we covered that lecture 3 or something, but it's okay. All right, so in DH method, you will assign a frame at each length, right? Which usually is the joint axis, then calculating end effective configuration to this intermediate frame, which is every frame with respect to the frame next to it. So we don't define a base frame. Well, we define a base frame, but calculation are not with respect to base frame. It's with respect to the frame before it. So that's the main difference. All right. That's the main difference in this method. Now, to find the transformation between frame T0 to N, 0 being your base, N being your end effector, you have to calculate T0 to 1, 1 to 2, 2 to 3, and then multiply all of them, right? There are a couple of assumptions. One, a chain consists of N 1 degree of freedom joints. So we will we saw that in the previous method. If a joint has a U shape, U joint, like 2R, we will separate those 2 R's. So those U to 2 R's, or if it's S joint, we will say there's 3 R's, but just put them on top of each other. So because they are rotating along a different axis, all right? They are numbered from 0 to N, 0 being the ground, N is your end effector, all right? You will attach the end effector frame to your N. N might be your last joint, but we are not including the kinematics of our end effector itself into this. So it's up to end effector, because you can have any kind of end effector. You can have a hand that has many degrees of freedom. You could have a fork that only closes and opens. So we are not discussing the end effector. It's up to end effector. We just place that on the last frame that we have. Okay. Joint variable corresponding to I joint is theta I. So first joint, theta 1. Second joint, theta 2. All right. Why we are talking about all of this? Because you will get a robot that doesn't have anything and you have to assign the frame. It's not like previous one that you get the frames. And this method is used when you want to actually assign the frames. Once we assign the frame, let's say we have all the frames, the goal is to create that expression. Now we are saying from one frame to another. So there are 2 methods here, but I'm following your book, is in appendix C of your book. If you're following the book, appendix C. And I'm using the book's example. So if you want to go back, we can study that better. So this says that from one joint I minus 1 to I, we will rotate, we can rotate around the frame, translate about another axis, then another translation, another rotation. This combination will take you from one frame to another frame. So our transformation matrix will be a multiplication of these 4. And these are about and along our principal axes. We already know how they look like. To make your life easier, this is the matrix that is correspond to that multiplication. So you don't even have to create those. You just need to grab this all the time. Yes.
So that first equation, is that saying the T of theta, or is it the T multiplied by 6?
Which one?
Is it f of x?
Here? Yeah, this is f of x type of thing. So it says that if you have a base frame, this is your robot, this is your end effector.
Look on the right side of that equation, though. It's
yes,
T
this is n.
Theta, not T multiplied by.
Hold on, this is frame 0. So this is T from 0 to n, okay, on the left side. These are all the angles, all the joints, variables that is between the 2 frames. We don't know what they are, so 0 to 1. Every one of these is a transformation from, for example, from 0 to 1, there's only one joint in there, so that's theta 1. The transformation between those 2 links, that every 2 links are connected with one joint, remember? So this is a transformation because of that joint's motion. Then theta 1, 2, then you go move to the next frame, between the 2 frames, until you go to the last one, so between whatever is before your end of it. So when we create this expression, we have a bunch of thetas, alpha I, that they are like we have theta I and di for join when they revolute or if it's prismatic. So we don't know how much they're going to rotate. It's a function of time, right? So this basically is theta 1 of t. Okay, I just drop all the t's because it's cumbersome. But when we say theta 1, we actually mean theta 1 of t. When we say d1, we say it is d1 of t. If it's a joint variable, is a function of time. To make your life easy, I usually put a star. This is star means that's a joint variable. It's a function of time. Okay. Did I answer your question? Okay. Now every one of those t's are equal to this multiplication. Now I call this big matrix. We're going to use big matrix every single time. for every one of those, we're going to create this. But when you code, you write this one time. We're going to create a table that represents theta I, di, all the variables. You just feed the table into it, and then it calculates everything. So all you have to basically code is this matrix and say, okay, multiply them now. But assigning the frame is the part that takes a little bit of work. All right, so calculation is pretty straightforward. So I'm going to call this big matrix. We're going to come back to it. So this is AKA big matrix. Now, when we look at this, we said that Ti minus 1 and I is a rotation along axis X, right? For angle alpha I minus 1. Look at here. We have alpha I minus 1, alpha minus 1. So once we have what alpha I minus 1 is, these are all going to be values. All right. What else? The translation about x-axis for AI minus 1. So you have here one time AI minus 1. Then a translation along z-axis for DI. You have DI one time showing up here, and then rotation about z and theta I, then you have theta i's. So actually there was another DI here. So once we have the values of these, this is just a simple 4x4 matrix. All right, now how do we get those values? How do we know from one frame to another how much we are rotating? What is alpha I, what is AI? These are called DH parameters. So for every frame, we have to identify DH parameters. We create a table, and then voila, we have the solution. So these are the steps to create the table, the DH table, and then create the expression. So creating the DH table is where it takes work. Now, we will assign joint axes. First of all, we will look at our diagram, how many joints are there, identify where's the base frame. Okay, that's frame Z, frame 0. And then, do you remember which axes are joint axes? Like for a revolute joint, revolution happens around which axis? Z. And if we have a prismatic joint, the translation happens about Z, right? So those are your joint axes. So it says that first find all the joints and then identify all the Z axes, basically. We have already done that for our previous examples and homeworks, right? You should be pretty comfortable doing that. So if you have a revolute joint, rotation about Z axis, and if you have prismatic joint, is translation along Z axis. Simply go and draw Z axis. Now that's the Z of that frame that you're currently in. So you will have, if you have 6 joints, you will have Z1, Z2, Z3, Z4, Z5, and Z6. You identify the direction. Okay. Now, after this, we are going to assign a reference frame. Now, from right-hand rule, if we know Z, if we find one of the other 2 axes, we know the direction of the third one, right? Because there's only one possibility. So we will find the direction of X. Y is a convention. They said if you find the direction of X, then Y will be, you know where Y is. We don't usually even show Y sometimes, we just show Z and X, and then Y is like implied where the direction of Y is. All right. Now, Z and X are going to play a role into defining alpha I and AI. Next, we have to find our DH parameters. Alpha I, AI, DI, theta I. All right. DI and theta I, you kind of know what they are. What do you think about theta I? What is theta I? So if you have a joint, yes, it's the rotation of that joint, is the joint variable. Okay. So if you have a revolute joint, we're gonna call the joint variable theta I. If you have prismatic joint, we're gonna call the translation di. So two of these are variables, these two. Two of them are constant, distance and angle between axes, all right? Now, there are cases that there will be a constant angle between two joints and there will be a variable added to it. We will solve your example for that. But in general, these two are the joint variable, the other two are constant values. Once we found our DH parameter or created the table, then we find the end effector configuration, which is pretty easy. If this was like 6, for example, well, 6 is too much, let's go to 3. Would be T01, T12, T23. Where do we find these T's from? Big matrix, yes, big matrix. Why? Because I already have all these values. I'm just gonna go plug in for every one of them and I have my matrix. All right. Now, di and theta, we said describes the, well, when it says links connection, that's the joint variable. Already wrote it here. So these are the fixed amount that we will see. Alpha I and AI describes the link itself, the configuration, how they are configured. Because you could have two links to be parallel, or the two links could be coincide or have some angles. How are we going to introduce this to our equation? Because it will affect the end effector position. That's through AI and alpha I. Derek, any question on Discord? No? You're on Discord like constantly? Yes, that's what I thought. I should have picked someone else. Yeah, it's like perfect excuse for him not to listen. It's like you said to do that. All right. So, so far clear what we're doing, the method. All right. So brace yourself for this next 2-3 slides. But if you get confused, don't worry. There is an example, simple example right after, which I'm gonna solve that. Things should fall into place. That's usually how it is. A little bit of confusing math, and then I show an example. It's like, oh, okay, could have showed us example first, but no. So this is a weird way of showing a robot link and join, but not all the robots have straight line links, right? So this just means that if link I was whatever weird shape, we don't care, okay? The distance between the two joints are important. Because well, these are all rigid body, right? So if you have a rigid body that is rigid in this way, there's a joint here. If this wants to rotate, these two will be the same as if they were connected with a link. We're not tracking the position of the link. We're tracking the position of our joint. So the distance, the perpendicular distance of these two are important. Okay, that's a key word here. The perpendicular distance between them. Now, if you have axis I think you should have written axis, right? Just one axis. Yeah, this is me not knowing English very well. Anyway, so if you have axis I and the next one, well, let's say I minus 1 and I, you're always checking the relative, right, between the two consecutive frames. So, first of all, what this axis is? Is it X, Y, or Z? We already said these are Z. So when I say axis I minus 1, I mean Z minus 1 and ZI. So you're gonna identify your Z's, ZI minus 1 and Z, and then find the mutual perpendicular between them, which is the distance between the two axes. Yes. Good question. So let's say they're not perpendicular, right? That's just one case. Let's see how many pens I have. Oh, 2. Oh, white and so if two axes are like this, can everybody see? What's the distance between them? The mutual perpendicular. You probably draw a line here, perpendicular to both of them, right? Then you say that's the mutual perpendicular between them. That's the distance we're looking for. We're not trying to find the distance between the two far points, right? We're actually trying to find the closest distance, which is the mutual perpendicular between them. That we will call it a I minus 1. Okay. Now, if these two are parallel, what's the distance? The same, just the same all the places. Ask the better question now.
What's the difference?
No. So they could be parallel. They could be distant. What is the other case? Where they coincide? What's the distance?
Yeah.
0. This happens all the time. When we have like S joined, that there are actually 3 R joints, they're all coincide, so all the distances are 0, right? So we will have 3 cases: parallel, coincide, and some weird shape. Well, weird shape, good luck, you have to find. Usually it's very clear from the diagram, okay? Most of the time, though, they're coincide or parallel. I assume I didn't hear that. Because we're talking about rigid bodies, right? Yeah, I didn't hear that. Okay. So AI minus 1 makes sense. The neutral perpendicular here is the keyword. Now, how do we find AI minus 1? Assume these two that are parallel, right? What's the twist between them? How much they're twisted with respect to each other? 0, right? So if they're parallel, the alpha I, the angle between the two z-axes is 0. Now, if I start rotating them, there is an angle between them, right? You can rotate them into it. Now, where do we measure this rotation about? So they could have rotation in this plane, or they can only have in this plane. Now, the convention says that we are gonna assume the rotation about x-axis. So you find the x-axis of this frame and see how much these two are rotated about that, and say, hey, alpha I minus 1 is that much. Okay, so if these two are on top of each other, if this was the x-axis, you're gonna find how much this rotated. So from going parallel to whatever this number is. And since we are defining x, we are gonna get the x in this direction. And then this will make sense, right? And then this will be the angle. So that's your alpha I, the twist between the two links. When we say link, we basically are talking about the joint axis that link is connected to. For theta I and vi, we already talked about it for prismatic and revolute joint. There is a special case for vi. I will show you through an example because this is not gonna make much sense. Let's work on examples to use all this knowledge. So identify all the axes, right? Then we are gonna get the x-axis. At this point, I'm gonna tell you where x-axis is, but x-axis we usually do as find all the z-axes. Okay, so z-axis I minus 1, z-axis I, then you find the perpendicular to them following the right-hand rule, because we find alpha I based on that. So kind of like they relate to each other. So purposefully, x-axis would be the perpendicular axis on the plane that contains these two guys. This is the axis. All right. For now, I'll give you x-axis, so we can create our DH table. So here's a planar robot. You have 1, 2, 2 thetas. All right. So that third one, that's just a end effector. This is not a joint. It's just a joint. End effector was there. We took it off, right? So that doesn't count. R, and then this, let's say B1, B2. All right. All the axes are assigned for you, but tell me where is Z1, where is Z2? Where's the Z1 is pointing out of the plane, right? That's your first frame. That's the second one, Z2. So both of them coming out of the plane. So this is Z2, this is Z1. Base frame is frame 0. So we start from 1 for joint. Theta 1 representing joint 1, theta 2 representing joint 2. Now we have to create our DH table. We have the direction of Z, we have the direction of X, they have been given. Okay, we'll discuss later with more example how to do that ourselves, but let's say we have it. Now we have to find the parameters. So that is your cheat sheet, how to find those. So you want to grab that and have it with you at all times. So I try to put it on all my examples during lecture, but if you are doing an assignment yourself, that's what you want to copy, right? Along with cross product. You know, everybody was looking for cross product equation on Friday. All right, so this basically says if you want to find ai minus 1, you have to find the distance between zi minus 1 and zi along xi minus 1, right? So it's a good formulation of how to find those. Things that you can do, you can create a table. That's the best way. So link I, and then alpha I minus 1, a I minus 1, they just look the same. Di theta I. We're going to fill this out. Now, how many joint do we have? 2. So we go from 0 to 2, right? Base frame is 0. We don't care about that. Joint 1 is 1, joint 2 is 2. So we have 2 joints. So our table is going to have 2 rows. So as many joints as you have, you're going to have that many rows. Now, what I'm going to do is I'm going to, for the first one at least, write down, for example, I equal to 1. I'm trying to find this parameter, right? They are DH parameters. DH parameter. So for this, A1 minus 1, 0. A0 is distance Z0, Z1 along X0. All right, now you have to find what that distance is. Let's go and look at our diagram. Distance between Z0, oh, sorry. This is my X frame 2, Z2, Z1, Z0. This is my second frame, this is my first frame, and this is your Z0, X0 frame. Now, distance between Z0 and Z1, what's this distance? B1. So this is B1. So this is going to be B1. A1, A0, because, sorry, alpha 0. Alpha 0 is angle Z0 and Z1 about X0. What's the angle between Z0 and Z1 along your X1? No, the 0, the angle between the two Z axes. They are parallel, the angle is 0, yes. Yeah, doesn't matter, thank you. 0, you can, let's just do that, because I think is that how I wrote my. As long as you feel under them properly, it's fine. So this is A. A was B1, this is 0, right? Now D is DI, I is 1. So D1 is distance X0 and X1 along Z1. So X0 is here, X1 is here. I'm going to draw it down below here. So this is X0. This is X1, right? And this is our Z1. What's the distance between X0 and XY along Z1? What's the distance between two coincide axes? 0. So this is 0. I'm gonna put 0. Now theta I. Theta I is angle between X0 and X1 about Z1. Take this out of here. So let's see, where is x0? So x0 and x1, this is your z1. So if you look at here, this is our theta 1, right? So at home position, your x1 was on x0, right? You're just showing there is a theta 1. So that this is a really good. So what's the angle? Theta 1. So now theta 1 is function of time, right? We don't know what it is. It's just a variable function of time. It is our joint variable. So if this was in home position, this robot, we will be here and here, right? We just moved it to show that these two are two joints that can move. Now, in home position, all of x1 is on top of x0, but now we can rotate. So since at home position, there was no offset between them, this theta is just the theta 1 star or the joint variable. So you just show it here. This is a theta 1 star. Now, we also know because this is a revolute joint, theta 1 has to appear. That's how where theta 1 appears. So if this was a prismatic joint, we know that we would not have a variable for theta. All right. Now, let's do this for joint 2. See if we can find that. Can you find all the DH parameter for joint 2? So we're talking, when we say joint 2, I equal 2, so you have A1, alpha 1, D2, theta 2. Since this is revolute, you know that your variable is going to be theta 2 star, right? Now try to find this variable, this parameter, sorry, not all variables. Yeah, yeah.
Or
You're
starting from the x before.
good question. So you are starting, you see that theta is drawn from here. So this is the rest position. So you're starting from there. Because if you were going below, then you had a negative angle that you had to consider. Yeah. Yeah, it just would be theta. So that is, so we are, good question again. We are only looking at the relative transformation between the two frames, right? We forget about what happened before because we're going to multiply this later. So we are only looking at these two frames. So we are only considering theta 2. Later on, when we multiply, all of them will get multiplied through the big matrix. Now, finding values. Some of them are a constant value. Some of them are variable. And effector. Sometimes I show an effector by EE. Did you find the parameter?
I don't think I'm right. So
I think you're right. But we can talk about it. Confusion is good at this point. Confusion is good because if you can clear it out, then you'll be set. The only time you have to work is to create this thing. Once you have it, it's just really no work to do. The star means that you just if I put a star, this means that this is a joint variable because you'll see that sometimes there's an actual offset. So like the configuration is somehow that there is a fixed rotation. For example, you'll have like 45-degree plus some variable, but in this example, it's just a theta star.
so it means it varies in time.
Now, hold on. Yes, that means that varies. I'm going to write it here. Well, at the beginning, write all these 4 sentences, right? So what is DI? Distance between x0 and x1 axis. Here, these two are one side. So there is no offset. So DI is the offset between links. you could have physically offset between link, and we need to consider that because it's going to create a torque. There will be a different velocity at the end of it. Right now, there are coincide, so there is no physical distance between them. There are examples that there is, and I think it's best when you learn through examples. Okay, so if you follow those 4 sentences or expression, you should be able to find the DH parameter. You always follow those 4 to fill this out. For every single joint, you plug in that I value and then just write down like I did, create, especially at the beginning. When you do a couple of problems, then you don't have to do that. You just fill this out. But for now, I suggest to do that. All right. So that side of the class I've been talking the whole time. Tell me what are the steps. I'm assuming you were discussing what the solution is. First one is B2. So A1 is B2. A1 is the distance between Z1 and Z2, right? They're parallel. The distance is B2. What is alpha 1? What is alpha 1? Alpha 1 angle between Z1 and Z2. What's the angle between Z1 and Z2? 0. They are parallel, right? There's no angle. What is D2? What is D1? Sorry. D1 is the distance between X1 and X2 along Z1. I'm going to draw that because, so this is X1, X2 along Z2, right? They are coinciding, so there's no distance between them, 0. What is theta I? So as we said, theta is the angle between, for this would be X1 and X2. X1 and X2, when you're trying to find the angle, you go find what is the home position. So your home position is here, and you see that this is your theta 2. So at time equals 0, what is that theta? 0. What is theta 2 at time 0? 0 when you're at home position. Let's say every minute, every second, we move 1 degree. Okay, what is theta 30? 30 degree, right? So starting from home position, and since we don't know what is time, because you're trying to write expression for kinematic, we are just representing it by a function of time, which is theta. I'm putting a star here to show this is function of time. So theta star is basically your theta t, right? Now, there are cases that when you are at home position at time 0, there is an offset between the 2 links. You have to consider that. But for this example, there are no offsets. It's a simple example to just help you to create that table.
So would it be more clear to say, like, would it be accurate to say that like these angles that are shown here are actually just functions of time?
That's what I just wrote. Yes. Yeah. It's correct.
If there was an offset of time 0, would you still just write theta 3 or would you write theta t plus?
When there is no offset, why do you put an offset?
If there wasn't.
If there's an offset, we have examples on Wednesday that there's an offset and you'll see. So we are going from a very simple example to just basically see how the main values are. Okay, there will be examples that you will have values here, all of them. Yeah. Which one? This one, right? This one? So alpha, so for I equal 2, or alpha is alpha 2 minus 1 is alpha 1, right? So alpha 1 is angle the I minus 1, I is to the Z 2 minus 1, Z1, and Z2, right? So Z2 is pointing out from the plane. Z1 pointing out of the plane. They're parallel. What's the angle between the parallel lines? 0. Okay. So the direction, yes. Okay, good question. So yes. 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 So I'm going to create a page here so I can. So let's look at this. Let's talk about the first joint, right? So this is theta 1. So this is our Z1 and Z0. So you're saying that why this distance is not E2 cosine of theta 1, right? So we are going to consider that our frame is here. Our frame moves with our link, right? We are trying to find along x0. So x0 is also moving when you're moving the links. So this is your x0. This robot at home position, Z0, Z1 was here. This is x0, okay? And then after some time, it went to this position. So our x-axis also moved with it. So when we are trying to find the distance, we are still finding along our x0. All right, so we don't find the projection. We measure along the axis. That's why those 4 sentences, I'm going to call them sentence, they're not, but I'm going to call them sentence. Those are really important, okay? We don't have time for the next example, but since Wednesday is just working through the examples, so these are some special cases. We are going to solve this example on Wednesday, and this was supposed to be your class participation. I'm just moving it to Wednesday. You don't have class participation today, but please come prepared on Wednesday. Remember those 4 sentences of how things work. Okay, I'm not going to review because it will take time. Thank you. Explain